All right, here we go for the last week. This is chapter 13. We are talking about solids. Solids are hugely important. A lot of stuff happens in the solid phase. Catalysis, a lot of catalysts are metals, and they're solids. When we talk about materials engineering, for all of you engineers out there, it mostly happens in the solid phase. So solids are really important. We're not going to cover them in too much detail. Actually, we're barely going to cover them in any detail. I'm only going to make a couple of videos on chapter 13. Okay, so let's first talk about what we call a unit cell. Oops. Let's get this out of the way for a minute. Okay, unit cells. And I'm just going to kind of give you a picture of what a unit cell would look like. First, we're going to just talk about two-dimensional. Okay, let's just do two-dimensional, like pennies. Okay, if we take a bunch of pennies and we put them next to each other and just pretend everything is, even and they're all the same size and all of that, and that I'm not a terrible artist. Okay, so if we have all these pennies here, first off, this is definitely not the most efficient way we could pack these, but we can have a unit cell, what we call a unit cell, that connects those 4 points, let's say. And what that unit cell is the smallest unit of this array, of this crystalline array, we'll call it, that we can just kind of slide along and reproduce the packing efficiency, or the packing. So if I were to reproduce that unit cell over here, I think you can see that if I were to just keep drawing these, what I'm going to do is I'm going to reproduce exactly, not exactly, but you know what I mean, that array that I've drawn over there of those pennies and the way they've been stacked. Okay, okay, that's terrible drawing, but oh well. You only have to deal with me for one more week, all right? So that is the unit cell. It's the smallest unit that we can draw, kind of repeat it over and over and over again and recreate the crystal. Now, like I said, that is not the most efficient way we can pack those pennies, okay? Because what we can do, I'm sure you can all figure this out, is here if we have a row of pennies, we can also stack the pennies like this. And that will give us a slightly different unit cell. And so every type of crystalline solid has a different unit cell. And this unit cell is very similar, but it looks like that. So if we reproduce it over here, it just looks like this. Okay. And then again, we can draw that unit cell over and over and over again, and we can recreate the way those pennies are stacked. Okay. So now, of course, when we move to 3 dimensions and talk about atoms, it gets more complicated. Big surprise. But here are the unit cells, or I'm sorry, not the unit cells. These are 3 of the unit cells. We're just dealing really, really simply. And what we have are simple cubic, body-centered cubic, and face-centered cubic. And we're going to take those one at a time and talk about them. Okay. First, let's take simple cubic. Let me see if I can zoom in on this guy. Okay, the simple cubic, if we look at it, let's see the best place to draw this. If we go from here to here and then to here, you can see that there are basically 2 portions of, or 2 radiuses there. So that's R, and then again here and here, R and R. That's the radius of the atom there. Okay. And the unit cells, these are the unit cells right here. The top is what we call the lattice array, and then the bottom is just, you know, the overall lattice with the unit cell kind of superimposed in there and dashed lines. So the simple cubic is the least efficient if we talk about packing efficiency and number of atoms. Let's first talk about number of atoms in that unit cell. Number of atoms. So each one of these little guys here that I'm going to highlight, think to yourself, think how much of a sphere that is. How much of an atom is that? Is that a quarter of an atom? Is it a 16th of an atom? Is it a half an atom? What is it? Well, it turns out that each one of these is 1/8 of an atom. All right. And how many of them are there? Well, there's the one I've highlighted already. 2, 3, 4, 5, 6, 7, and back there in the back corner there are 8. There's 8 corners, so it kind of makes sense that there's 1/8 of an atom on each corner. So how many total atoms are there? Well, that's 8 times 1/8. Somebody Google that for me. That's 1 atom per unit cell. Okay. And if we were to do some math, figure out the volume of the cube and the relative volume that is taken up by those atoms, we get what we call a packing efficiency. Okay? And packing efficiency is simply how much of the space is occupied by the atoms. And the packing efficiency on the simple cubic is 52%. Okay? So just a little bit more than half of this unit cell here, just a little bit more than half of that is taken up by atoms. The rest of it, the 48%, is empty space. It doesn't have to be empty space because, let's just pretend for a second, all of these are cations, all the atoms on there are cations. There's a little hole in the middle there. You can drop an anion. Actually, it'd be the other way around. Let's pretend that all the corners are anions because they're large. We can take a little cation, because remember cations are smaller, and we can drop a little cation in the middle of that, and that is kind of, we can begin to understand how ionic compounds are put together. Okay, let's go to the body-centered cubic. Let's talk about the number of atoms in the body-centered cubic. So again, we have the 1, 2, 3, 4, 5, 6, 7, and then in the back there's an 8th there that we can't see, so that's 1 atom. And then this green, the reason it's called body center is because there's an entire atom that is inside the cube. Okay, that sphere is entirely encompassed by that cube. So that's 1 plus 1, that gives us 2. So there are 2 atoms there. Now we can see that this is definitely more efficient than the simple cubic. There's a higher packing efficiency because there are more atoms. And this gives us a packing efficiency of 68%. And again, we're not going through the math, but we could. Okay. And then let's talk about the packing efficiency for this face-centered cubic. Okay, and face-centered cubic, if we look at it, look at the green atoms here. Look how this atom is sliced right in half. Okay, so that is 1/2 of an atom, and each one of these little green guys is 1/2 of an atom, or a sphere, whatever you want to think of it as. Okay, and now and that's why it's called face-centered. It's like the face of the atom on the edge of that cube. So there are 6 of those. There's 6 sides to any cube. So 6 times 1/2. And then we also have our 8/8. So that's 1. So that gives us 4 atoms in this face-centered cubic. And now I think you can see that that is probably the most efficient of these 3. And that has an efficiency of 74%. Okay. And like I said before, this is by no means comprehensive. We are definitely not covering everything in terms of cubic unit cells, but that's just an introduction. Okay. And in the next video, we'll do a calc. Yay!